All right, this is part 2 of the review for the final exam, summer 2017. So we're looking at solving the equation for number 10, and it's an absolute value, so we need to make sure that we isolate the absolute value before doing anything else. So we'll add the 2 over, which would make this 12. We also want to divide by 3. So this is x plus 1 and an absolute value, and then this would now be equal to 4. When you're dealing with an absolute value, remember there are 2 different possibilities for what could make the inside part have an absolute value of 4. We're not saying that this 4 is ever going to turn into a negative 4. It's actually always a positive 4. But what we say when we solve this is that the argument inside could have either been a negative 4 or a positive 4 before you took the absolute value and got 4. So we set up the 2 possibilities. X plus 1 equals negative 4 and x plus 1 equals positive 4. Solve them both for x, so this would be negative 5 and this one would be positive 3. Number 11 is a square root equation. For these, we also try to isolate the square root first, so we're going to move that 4 over since it's not underneath the radical. So subtract it over. Now, to get rid of a radical, we raise it to the power that would cancel it out, but when you use the power rule, that's what that's called, you create sometimes extraneous solutions. So all radical equations need to be checked at the end to make sure the answer actually works, because you get your solutions that do work plus sometimes extras. So we do need to be careful about that. So if we square both sides here, so I'm going to use the red just to indicate that I'm squaring both sides. On the left, it's just going to make that 2x minus 5 because the square and square root would cancel out since they're opposite operations. But on the right, you have to FOIL it out. You have to write x minus 4 times x minus 4. So this would be x squared minus 4x, so that'd be minus 8x. Negative 4 times negative 4 would be positive 16. Gather everything on one side since this looks quadratic. So we would subtract the 2x over, making that negative 10x. We would add the 5 over, making that positive 21. And then that does factor into an x minus 7 and an x minus 3. So we have 2 possible solutions, but we don't want to circle them yet. So we're going to go over here and do our check. So we're going to check 7 first. 2 times 7 minus 5, and then plus 4 equals 7. 2 times 7 is 14, minus 5 would be 9, so that's square root of 9, plus 4 equals 7. Square root of 9 is 3, 3 plus 4 does equal 7. So 7 is a good solution. It does work. And then we plug in 3 to check. Make sure you plug it in for all the x's. This would be 6 minus 5, so that's square root of 1. Plus 4 equals 3. Square root of 1 is 1. 1 plus 4 does not equal 3. It equals 5. So this would be an extraneous solution, and we would mark it out. For number 12, we're looking at solving the inequality and expressing the final answer in interval notation. It's an absolute value inequality. For these, it depends on 2 things, whether or not you can, first of all, solve it, or if it's going to be a special case like all solutions or no solutions. That has to do with if a negative shows up on the right side, and then you have to determine whether or not it's no solution or infinitely many, or like we like to say, all real numbers, based on if it's a greater than or a less than. In other words, does it make sense? If you get a positive on the right side, once you've isolated the absolute value, it depends on if it's greater than or less than on how you solve it. So I'm going to first of all isolate the absolute value. So we'll subtract the 1 over. So that would make that 6, and then divide by 2. So that this absolute value symbol really is by itself. So that now has our final format before trying to solve. As long as the number on the right is a positive number, you will be able to solve, but you have to know whether or not you're going to set the argument in between the negative and the positive, or if you're going to have 2 cases going in opposite directions. With absolute values, the less than a positive number is when you put it in between. So this part goes between the negative and the positive. That's if you have a less than case. If we have a greater than case and a positive number on the other side, we're going to have 2 different scenarios, one going to negative infinity and one going to positive infinity. So we're dealing with the two different directions now because we are looking at a greater than and a positive 3. So the first case is that you can just write it without the absolute value. In other words, the argument really is greater than 3. The other case, which is an OR, is that the argument is going to be the complete opposite. So it would be you flip the inequality and you change the sign. This will give us the headed towards negative infinity case as long as there's no weird sign changes. Oops, sorry, I didn't mean to write negative infinity. Talking and writing at the same time. Negative 3. We still use that number from the right side. So notice exactly what the problem was, but just removing the absolute value, and then you keep the left side, but you change the two other pieces. So if we solve this first one, we would add 1, so that's 4, divide by 3, so greater than 4/3. This one we would add 1, so that would be negative 2, and then divide by 3. Since we're not dividing by a negative, this still stays a less than. Now, when you're writing this, you wanted an interval notation, so the less than case should be the smaller case. So this would be negative infinity up to negative 2/3. We're using a parenthesis since there's no equal to bar, union with 4/3 to positive infinity, because that one is greater than 4/3. And that would be our solution for number 12. Okay. For number 13, we're dealing with a rational inequality. This is going to require the sign chart method to make sure we are checking to see whether or not certain aspects of this fraction having an x in two locations on a numerator and a denominator, whether or not those signs, when they're worked out, are going to end up making something greater than or less than another number. So the hard part about this is that a lot of students want to use cross multiplication to solve this, and I've even seen some people teach it that way, but that's not actually true. You don't cross multiply with inequalities, you cross multiply with equations. So the best bet for solving this one is you actually want to move everything to one side and get it set greater than or equal to 0. So if I move over that positive 2, it'll be subtracted. And I go ahead and put it over 1 because I do see that I'm going to have to get a common denominator. I would multiply this one by 3x minus 5 on top and bottom to get the common denominator. So this is going to be x on top, and then we need to distribute this negative with the 2. So negative 6x and positive 5 all over 3x minus 5 greater than or equal to 0. Clean up the top, that would be negative 5x plus 5 over 3x minus 5 greater than or equal to 0. So now we're going to have what we call two or more critical values. Critical values happen on any factors that are on top or bottom. I always separate my top from my bottom because I'm going to have different rules on whether or not it's going to be a parentheses or a bracket based on its location and the symbol out here. Denominators are always going to be open regardless of whether or not you have this equal to bar. So the critical value for the bottom, think about setting this equal to 0. We would add 5 and then divide by 3. So 5/3 is going to be a critical value for the bottom, and it's going to be open like a open circle or a parentheses, okay? And that's just any denominator always has to be open. You do not want to be equal to 0 because you'd be dividing by 0. And then for the top, we would set negative 5x plus 5 equal to 0. That is 5 equals 5x or x equals 1. So 1 is going to be closed because the top always obeys the actual symbol. So since there's an equal to, it's going to be closed. The next thing I do is I place those numbers from least to greatest on my number line, and I actually do a test value in each side to see if this comes out true or false. So and always place them from least to greatest. So 1 is actually smaller than 5/3. We want to pick so I'm going to write my intervals out. First of all, go ahead and put markers. This is a closed, this is an open. That helps me know if I'm bracket or parentheses. So negative infinity to 1 with a closed, so a bracket. 1 with a bracket to 5/3 with a parentheses since that's open. And then 5/3 to positive infinity. When you pick your test value, you have to make sure you are picking numbers that are actually in the intervals. Otherwise, it doesn't make any sense. So less than 1, I could pick 0. Between 1 and 5/3. Well, 5/3 is 1 2/3, which is like 1.6 repeating. So maybe we pick 1.2. And then something bigger than this would be maybe 3. Just something in each region. Excuse me. You put your factors that your critical values came from, and I'm going to have to erase some stuff because I'm running out of room. Give me just 1 second. So these top and bottom factors are going to be our parts that we're going to be testing our signs on. Now, if you wanted to write down the actual work for all of these, you could, but you really only need to know the signs, because when you divide, positive times positive, or positive divided by positive is positive, positive times negative or divided by negative is a negative. Those sign rules are the same for multiplication and division. So if we plug in 0, we get a +5, so that's a plus. We plug in 0 to the second one, we get -5, so that's a negative. A positive and a negative make a negative. 1.2 times -5, so 5 negative times 1.2, and then that's -6 plus 5 would be negative. 1.2 times 3 is 3.6 minus 5. It's going to be -1.4, so that's a negative. Two negatives make a positive. This would be -15 plus 5, that's going to be negative. And then 9 minus 5 is going to be positive. So that's a positive and a negative, which makes a negative. Whether or not which regions, you're going to either use all the negatives or all the positives, and that's dependent on this. And this needs to be on the left and this needs to be on the right for this to actually make sense when you read it. We want things to be greater than or equal to 0. So that means we want positives. So the only solution is going to be this middle column. And that's it. So that's the solution in interval notation. Okay, let's look at number 14. Number 14 is an application of some formulas that we had to learn, just like the quadratic formula, but this is distance and midpoint. So remember, if you have an ordered pair and another ordered pair, you can find the distance by taking kind of Pythagorean theorem, and we do x2 minus x1 squared plus y2 minus y1 squared, and all of that's underneath a square root. So this would be 6 minus 4 squared plus 2 minus -3 squared. That is going to be 2 squared. This would be plus plus, so that's going to be plus 5 squared. So that squared is going to be 4 plus 25, and you need to work this all the way out. So this is square root of 29. If this has anything that's a perfect square in it, we would want to break that down and work it out. But since it's not got any perfect squares that go into it, the part A is going to be square root of 29. The midpoint formula is a little different. You average the x's, you cut them in half. You average the y's, so we're adding them and cutting them in half. So add them and cut them in half. You average them. So 4 plus 6 divided by 2, and -3 plus 2 divided by 2. This comes out as an ordered pair. 10 divided by 2 would be 5. That's -1/2. So we just leave it as a fraction. So there's my midpoint. For part C, we're finding the equation of the line through these 2 points and then writing it in slope-intercept, y equals mx plus b. So we need to find the slope first using our slope formula, y2 minus y1 over x2 minus x1. So this will be 2 minus -3 over 6 minus 4. So that's 5/2. Then we use our point slope formula. Anytime you're trying to go from a piece of information like slopes and points to a formula like slope-intercept or general form, which sometimes is called standard form, you usually need to use point slope as a mediation. You don't have to. Some people use the y equals mx plus b, but I find that this one's easier to transform into lots of formats. So for us, we need to look at this and plug in what we know. So we can pick any of the points that we have, A or B. So I'm going to pick B, and then we plug in our slope as well. So y minus 2 equals 5/2 x minus 6. Since 2 divides evenly into 6, I'm just going to go ahead and distribute. So this would be 5/2 x. That's going to be negative 30 divided by 2, so that's negative 15. And then we'd want to add the 2 over to get this in slope-intercept, which gives me negative 13. So there's the slope-intercept form. D is a little bit different. You want to find the perpendicular bisector. There's two words there, and they both mean something that you need to do. Perpendicular means we need to have a perpendicular slope. So we already know the slope of the old 2 points. Slope of A and B is 5/2. So a perpendicular slope would be the opposite reciprocal. So we flip that and we change the sign, so negative 2/5. The word bisector means that when you go to do point slope, you can't use just any old point. You have to go through the middle of AB. So we need the midpoint. And we did find that. The midpoint is 5, negative 1/2. So we take our point slope formula, y minus y1 equals m parentheses x minus x1. I would go ahead and make that y plus 1/2. I might as well go ahead and distribute here. This is negative 2/5 x. That'd be positive 10 over 5, so that's plus 2. Let's get rid of all the fractions because we're going to general form, and in general form your ax plus by equals c with no fractions. And usually the leading coefficient also needs to be positive depending on your textbook. So I'm going to multiply everything here by 10 to get rid of all my denominators because 2 and 5 both go into 10. So this would be 10y plus 10 divided by 2 would be 5. Negative 20 divided by 5 would be negative 4x, and 10 times 2 would be 20. In general form, we need to get the x on the left with the y, so I'm going to add it over. So 4x plus 10y, subtract over the 5 equals 15. So there's that. So for number 15, we are doing some evaluations with functions. We're especially doing the difference quotient. Different people handle this in different ways. I like to think of the top as two separate pieces that I can work out on the side, specifically since this is a new concept for many students. When you get a little bit better at this, you just do it all in one line and work it out. But if we find these two pieces, then we can just put it on over our h. And this is our function right here. So I need to do f of x plus h. What that means is wherever there's an x, you're going to replace that with the binomial x plus h. So we need to write that twice because it's being squared and FOIL it. So that's going to be x squared plus xh plus another xh, so that's 2 xh's plus h squared, and we want to distribute the 4 there to that parentheses. So I'm going to highlight this because this is my yellow piece. What I just found here is this top first part. Then I'm going to do the second part, which is negative f of x. This one is always a little bit quicker. This just means negative 1 times your function, which is 4x squared minus 5. So it just changes all of your signs. So that's my blue piece. Now that's not our final answer because this is just me working out the two individual tops. So my difference quotient is going to be the yellow on top first, and then the blue. You don't need to write minus because we've already taken care of the negative sign, so it's already been done, all over h. Now there should be some things that cancel out. So we have the 4x squareds are gone, the negative 5 and positive 5 are gone. This is 8xh plus 4h squared over h. And if we pull an h out of the top, it will cancel with the h on the bottom. So the final thing reduces down to 8x plus 4h. Okay. And then 16 will be the end of part 2. 9 through 16 were all problems that, actually no, I'm going to go to 18, sorry. Okay, so we're going down to number 18. Sorry, I stopped for a second just to make sure. 16 is from section 3.4 as well, the function section. We're looking at finding the domain of the following function. What we learned about is that certain functions are just assumed to have an implied domain of all real numbers. Things like absolute value functions, polynomial functions, cubed root functions, in other words, odd root functions. But there are two types of functions we talked about specifically that cause us grief. The ones that have even roots, like fourth root, squared root, you can't have those insides going negative because we'd be dealing with something that's not a real number. And then we have the things that are rational, which means they have x's in their denominator, which means we could have things that make us divide by 0. This problem has both. So we have to consider what would keep the top from being imaginary. And to do that, anytime you have an even root, you set the inside part greater than or equal to 0 to make sure that it does not go imaginary. So we'd add the 3 over. And that says that right now we have to stay greater than or equal to 3. So if you think about a number line, we're not going to do any sign charts, but here's 3 on the number line. We have to shade to the right of 3. That's our domain right now, just looking at the top. So nothing less than 3 can work, okay? And then in the bottom, we see that this factors. This would be x minus 8, x minus 5. So x cannot be 5 or 8 because that would make us divide by 0. What you need to check is to see if 5 and 8 actually fall on that shaded part, and they actually both do. So 5 would be right here, and 8 would be a little bit further down. So we have these two restricted values that are showing up in our shaded region. So we need to remove them by leaving them out as open circles or skipping them in our interval notation. Now if one of them had fallen over here on the left side, we would just ignore it because this part is not shaded anyways. So this is 3 to 5 with an open circle, so open parentheses, and then 5 to 8 because that's another little region, and then 8 to infinity. And that's it. That's my domain. Okay, so let's look at 17. 17 came from section 3.5, graphing using transformations of functions. So we learned that square roots have a specific shape. We had what I called the parent graph. And the parent square root of x, just that typical square root of x, square root of 0 is 0, so you get this point right here. Square root of 1 is 1. And we don't want to do square root of 2 or 3 because those are not perfect squares, but square root of 4 is 2. Notice I didn't do any negative x's because if you plug in a negative, you're going to get an imaginary number. So it had to be starting at 0, greater than or equal to 0, and going to the right. Now, transformations can switch what this parent looks like. We can have shifting up or down, right or left. We could reflect upside down or across the y-axis. We could either stretch or compress. So depending on what you have in your actual function will tell us what we're doing. Anything inside is going to be what we call a horizontal shift if it's added or subtracted here. Now if there's a number in front of the x, that's different. That would be a stretch or compression. But if they have something added or subtracted inside that parent part, the square root of x, it's a horizontal shift. And horizontal shifts, you always do exactly the opposite of what you see here. So since they subtracted 4, to recenter, we would need to think about adding 4 or going right 4. Okay? If you have a number added or subtracted at the end of a function, so after the parent part, so after the square root, that's going to be what we call a vertical shift. And that's going to either move us up or down. And it's happening to y, whereas this was affecting our x, this is happening to our y. Anything that happens to y is exactly what you think. So it's going to be up 2 since it's positive. The number in front of my square root of x is a 1, so I'm not stretching or compressing, but I do have a negative. If you have a negative in front, you're going to reflect over the x-axis, which means upside down essentially. If you had a negative in front of your x inside, you'd be reflecting across the y-axis. So for us, we need to take each of these 3 points and do these 3 transformations. And you always want to work closest to x out. So vertical shifts usually end up being the last thing you do because they're the farthest away using order of operations. So 0, 0 needs to move right 1, 2, 3, 4. Flip it over the x-axis. It's already on the x-axis, so we can't flip it. And then up 2. So there's its new location. 1, 1 needs to move right 4. So right 1, 2, 3, 4. Flip over the x-axis, so now it's down at -1, and then up 1, 2. So it ends up right here. And then for this last one, we need to do 4, 2. So 1, 2, 3, 4, up 2. So that's where this one is now, but we're thinking of our original point. So we need to go right 1, 2, 3, 4, reflect it down over the x-axis down to -2, and then up 2. So it ends up being right on the x-axis at the next tick mark. So this is now an upside down version of this parent that's been shifted right 4 and up 2 as well. So that would be my sketch. And then the final one, and 18 is the end of Unit 2. So these part 2 of the video all came from Unit 2 of our class this semester. This is a piecewise function. To do a piecewise function, I always think of it as each row is its own equation, and we're just graphing it on a limited domain. So -2 to 1, and then we'll graph y equals x minus 3 from 1 to 3, and then we'll graph y equals 4, which is a horizontal line, if x is greater than or equal to 3. This helps me set up my tables, because I just do a quick table of values for each one. Some people do these by transformations. Doesn't matter as long as you know how to handle the domain. So -2 to 1. Even though this is not an equal to, you do want to include the endpoint in your table so that you have a place to put an open circle, because if it doesn't have the equal to, it's an open circle. If it has the equal to, it's a closed circle. Anything in between is just going to be points. We're not really distinguishing open versus closed, even though they're closed. So you should only have open circles or closed circles as distinguishing factors on the endpoints. So -2, 0, and 1. I'm just doing enough to get a picture of what this looks like. So -2 is going to be open because of the non-equal to, and then 1 is going to be closed. Everything in between is just going to be connected. So if we square -2, that would be 4. 4 times 2 is 8. Square 0, that would be 0, times 2 would still be 0. Square 1, that would be 1, times 2 would be 2. So -2 up 1, 2, 3, 4, 5, 6, 7. I need another line. 8. Graph was a little bit shy. So there's that first point, and it's supposed to be open, sorry. So there's my first point. And then 0, 0. And then 1, 2. And that one is closed. So this is just a part of a parabola. Okay. All right, for the next graph, we're going from 1 to 3. So make sure you at least get one point in the middle if you can. And these are both going to be open endings. So open on both far points. So 1 minus 3 is -2. 2 minus 3 is -1. 3 minus 3 is 0. So 1, -2, open. 3, 0 is also open. And then we have that point in the middle, and it's just connected, so it's part of a line. And then the last one is for 3 and greater. So even though this will keep going forever, I only do a few points. Just remember not to have any other endpoint. You just keep going. So this would be closed because it is equal to, and this has no x to plug into. The y is always going to be a 4. It's horizontal line. So 3 up to 4, closed circle, and then this is just always flat forever to positive infinity. And that's the end of this video for part 2.